Cosinus.
Yeah, you have to use, just as you did, you have to use the cosine rule, just as we did in the previous case, right? So in this case, we'll say here, theta 3, because this angle here will be pi minus theta 3. Okay? So r square will be equal to a2 square plus a3 square minus 2a2 a3 2a2 a3 cos of pi minus theta 3. Okay? So this will be equal to, r square will be equal to a2 square plus a3 square plus 2a2 a3 cos theta 3, or cos theta 3 will be equal to r square minus a2 square minus a3 square divided by 2a2 a3. Or we can write, okay, what is r? How do I find r? Because we need to know r, right? How do we find r?
Root of x square.
Yeah, from here. So r from here, obviously r square is equals to x square plus y square. Okay? So we can say that cos theta 3 will be equal to x square plus y square minus a2 square minus a3 square divided by 2a2 a3. Alright, so here you can say theta 3, because it's cosine, you'll say plus or minus cos inverse of Now that leaves us with finding theta 2. Right? So how do we find theta 2? Huh? How will we find theta 2?
The same method.
You can use exactly the same method and find the same thing. So you will do again theta 2, find using, you can use, I'll leave that to you, find using cosine rule. Or you can do the same thing as we did previously in the case. See, the diagram looks a little different here, but if I draw the same thing, it will look like a 2 degree of freedom manipulator. So in this case, I have pointed it down like this. Let's say I draw it like this. This is exactly like a 2D of manipulator, right? A 2D of manipulator was like this. And we solved it like this, okay? So this is the elbow down configuration. This is the elbow up configuration. Okay? Which is why you get two solutions. The first diagram was this, reaching the same point P. Okay, so you'll get two values. That's why you have plus or minus. In this case, in the case of a 2DOF manipulator, theta 2 was plus or minus. So this is minus theta 2, and this is plus theta 2. In this case, because the last joint is theta 3, so this will be plus or minus theta 3. You'll get exactly like this. I'll go up, I'll go down. So only thing, here you found theta 1 like this, here you have to find theta 2. So do the same, exact same steps. You can first find out what is, last time what we did was, we found out what is alpha, find what is beta, and do it. Or you can find directly using cosine rule, because you know A1, A2, and you can find theta 2 from there. All right, let's move on to doing, okay, one thing that I have to tell you is a few special cases. I'm sorry, let's do that first, and then we'll continue. Okay. In this case, this is not the only solutions that you will have. Sometimes you will have a case like this. What happens now? What happens now in this case? So in this case, because it's on Z, P will be like this. I'm sorry. You'll have Z, but X and Y will be 0 because they are exactly on the origin, 0, 0, and you'll have only Z. Right? So, what does that mean? How do you find theta 1 in this case? You get 0 over 0, right? So in this case, this point will remain constant even if the manipulator rotates along theta 1, right? If you hold these two constant at some degrees, okay, let's say that both A1 is equal to A2, in that case this angle will be equal to this angle because the opposite sides of this triangle are the same. So these two, if I hold them constant like this, and if I rotate theta 1, this will be 0 because the point will remain constant and it will go around. So theta 1 will have infinite solutions. Right? Because for any value of theta 1, the point is not going to change. It's going to remain there. Only thing is the orientation will change, but we are not concerned about orientation. At this point, we are only trying to track the position px, y, z. So even if I rotate theta 1 like this, the manipulator will rotate, but it will still stay at this point. Okay? So in this case, it will have an infinite number of solutions. So you have to look at some special cases. Another thing is, let's say that I have the manipulator like this, and I'm trying to reach this point, right? This is, let's say I'm trying to reach, for example, I'm trying to reach this point. Now I can reach it with this value of theta, or I can completely go here by a pi by 2 and then fold over like this, okay? So theta 1 will always have two values. It will be theta 1 and theta 1 plus pi, because you can always come to this point by rotating this totally by plus 180. So this will be on this side and then fold over like this. So you have to consider a few more special cases in the case of an articulated manipulator. So this is a case where it has infinite solutions, and also this value of theta 1 that you find out as y over x, tan inverse of y over x, is not unique. You can have another solution which will be plus pi.
Professor,
So
can you explain this one
this
more
one,
time?
sure. So I'll tell you, let me give you an example. Okay, so it's a little difficult to visualize, but bear with me and hopefully I'll be able to let's say that we have a point here. All right. Now what I want to do is, this is a set value of theta 1, okay? So let's say that this is theta 1, I'm going here, like this. I want to turn this completely opposite by pi by 2, which is here, okay? And then move this arm like this. Understood? So theta 1 is, when theta 1 is here, I have to go like this. Like this, right? What I'm going to do is completely turn theta 1 by pi by 2 and move the arm here, like this, then move this back here. Okay? So what will happen is, this will be like that, okay? I'll bring it from here and move it like this, okay? So basically it is, I can reach like this, or I can move that completely to the opposite side, but theta 2 I'll have to fold here, okay? Alright, now let's go to a inverse kinematics of a 3 degree of freedom manipulator. I'm going to give you a homework to solve these kind of problems, and we'll also do a lab that will involve this. But let's move to doing kinematic decoupling. Kinematic decoupling is nothing but, we do this as inverse kinematics for 60 manipulators. Okay. So as you know that 3 degrees of freedom is complicated enough. When you try to do 6 degrees of freedom, it becomes even worse because you cannot draw everything. But what we say here is, we'll consider a manipulator with a spherical wrist. Manipulators with a spherical wrist. Okay, so you have 3 degrees of freedom for positioning. Okay, 3 degrees of freedom for positioning. Let's say theta 1, theta 2, theta 3. And 3 degrees of freedom for orientation. Okay, this will be theta 4, theta 5, and theta 6. All right. Now, the reason we do this is because we'll assume the following. We'll assume that the first 3 degrees of freedom, this is responsible for positioning the arm, and the second one only changes the orientation. Okay? Usually, this is true of industrial manipulators because these 3 will control the X, Y, Z. This will give you X, Y, Z. And this will control the theta, phi, theta, and psi. The orientation. Okay? So when you look at the end effector coordinates, in the last part we were talking about P, X, Y, Z because this defines the position of the end effector. But now, because you have to find out 6 values, we talk about an end effector position is defined by eta. Okay? Eta is the end effector position. It is given by X, Y, Z, phi, theta, and psi. So this is the position and this is the orientation. Okay? So given this, given eta, which is the end effector position, and orientation, given this, we need to find Q, which is theta 1, theta 2, theta 3, 4, 5, and 6. Okay. The way we do this is we'll decouple them. Okay, what do you mean by decoupling? We'll treat the position differently and we'll treat the orientation differently. We'll say that the first 3 degrees of freedom will control the position, the next 3 degrees will take over the orientation. Okay, so we'll separate the two. So let's think of a manipulator like this. This is my wrist, which has 3 degrees of freedom here. All right, this is a spherical wrist. If you look at a DH table, wherever you have a spherical wrist, at the end you have a end effector tool length, which is D6, and you have the end effector length, right? You have written so many DH tables, at the end you have a short length, which is the tool length, which is D6. Okay, so this is the spherical wrist. Let's call this point as WC, or the wrist center. Now, this is θ1, here θ2, let's call this as θ3. In this you will have θ4, θ5, θ6. Okay. So how do I find all of them if I only know eta? Eta is the end effector position and orientation. The way we do that is, we'll start off by defining the wrist center. So what we'll say is, if I know the wrist center, the position of the wrist center is defined by θ1, θ2, θ3, right? θ4, θ5, θ6 have nothing to do with the position of wrist center. They only change the orientation of the wrist. Because if θ4, 5, 6 moves, it will only move this. It will move the wrist. It will move the end effector like this. It's not going to change WC. WC will remain where it is. It will only change the end effector, right? So if I'm changing any of the 3 angles, any of these 3 angles, it's only going to change this point, right? If this is D6 at this point. That's all. This will define where WC is. So if I find WC, I can solve for θ2, θ1 and θ3, just as I solved for a inverse kinematics of a 3 degree of freedom manipulator. So given this, for the first step we need to do is find WC. So to do that, we'll first start off with defining the orientation. The orientation is given by the angles phi, theta and psi. Okay? So we'll construct a orientation matrix R06, because this is the final orientation, based on the angles phi, theta and psi. How do I construct a rotation matrix based on 3 angles? How do I do this? It's your choice. You can pick either this to be Euler or you can pick this to be RPY. Okay? So for example, let's say this is Euler. Then R06 will be Z, P, Y, theta, ZYZ, right? Okay? So that is how you will construct a rotation matrix. Once you define the end effector orientation, this is defining okay, this is your step 1, you will define the orientation. Alternatively, you can also construct R06 as RP1, okay? This is fixed frame, this is current frame, okay? It depends upon how you want to use it, it makes no difference with the outcome.
Professor, theta 4, theta 5 and theta 6 affects the position of the end effector or only, or affects the position and orientation of the end effector?
Okay. We will assume here that given px comma y comma z, right? If I change θ4, θ5, θ6, the wrist center will not change. The end effector orientation will change. The center, this point remains constant, right? Because at this point you have 3 joints concentrated at the wrist center.
So it only affects the orientation.
It will affect XYZ. It will affect XYZ. But the problem is, it will not change WC. WC is controlled by theta 1, theta 2, theta 3, right? So for example, if I move my arm here, right? If I change these two joints, then the wrist will change,
Wow.
right? If I only change this, the wrist center is constant, I'm only moving the hand, right?
Okay.
Okay, so I'm keeping this point, this is my wrist, I'm keeping this point constant. These two will define where this point is, because changing this is not going to change the position of the wrist.
Okay.
Okay, so theta 4, theta 5, theta 6 is not going to change WC. WC will remain constant, it's only going to change the orientation of this. Alright, so once you construct this matrix, we need to find WC. So what we do is we work backwards. So from here, if this is my wrist, okay, and I know this point, x comma y comma z. All right. From here, we know that the orientation is defined by R06. I want, and I know D6. I want to come back to WC. Okay. I want to work myself from here to this point. So we do, step 2 is find the wrist center. Okay, find the wrist center WC. So to find the wrist center, we find wrist center. The book uses letters OC, but we'll use it as WC. WC will be equal to x comma y comma z, which is the end effector coordinates, minus D6 R06 Why do I use 001? Why do I use 001? Anybody? Why do we multiply that by 001? Because D6 is measured along the z-axis. Okay, this is a vector along the z-axis. In the final frame, D6 is measured along z5. So 001 means this is along the z-axis, and obviously it will be multiplied by the orientation because you want to undo this orientation. So what you'll do is you'll subtract, multiply this by the orientation, and you'll subtract it from this. This will lead us to WC, which is nothing but, let me write it like this. This is the wrist center. So once you calculate the wrist center, find theta 1, theta 2, theta 3 using 3DOF position So we'll find theta 1, theta 2, theta 3, just as we find the inverse kinematics, like the examples we did before. So once you find theta 1, theta 2, theta 3, you'll forget about the wrist. You'll only consider this to be a 3 degree of freedom manipulator, and you can find theta 1, theta 2, theta 3. You'll think of it like this. This is XC, YC, and ZC. So this is a problem like the earlier two problems that we solved. You can find theta 1, theta 2, theta 3. So this will solve the position part. Okay, this is the position. Okay, so you can find theta 1, theta 2, theta 3 from the wrist center coordinates. We are not talking about orientation. The next thing is, how do we find 4, 5, and 6? To find 4, 5, and 6, we'll do one thing first. Once you find theta 1, theta 2, theta 3, step 4 is find R03. Okay, step 4 is find R03. How do we find R03? From, if you know theta 1, theta 2, theta 3, you can find T03, which will be equal to A1 times A2. Let me write it like this. A1 of theta 1 so this will be equal to T03 will be equal to this will be a 3 by 3 matrix, and this is the position, and you'll get this. So this is what we need. We need R03. Okay. So once we find R03, next is find find R36, because R03 is a function of theta 1, theta 2, theta 3. R36 is a function of, this is a function of theta 4, theta 5, theta 6. So to find, we'll write it like this, R06 will be equal to R03 times R36, right? We know this from here, like this. We know R06. We know R03 from here, okay? So let me write it like this. We know this from here. And we know this from here. So we need to find R36. So we'll multiply this by the inverse. You want to get rid of R30. I'm sorry. Okay, so here we'll have R03 inverse. Okay, let me do it in one more step. That's fine. R03 inverse times R06 will be equal to this will be your identity matrix, I 3 by 3. Okay. Now we also know that for R inverse is equal to R transpose. For a 3 by 3 matrix, R inverse is equal to its own transpose. So here we can say that this will be equal to R03 transpose times R06 will be equal to, or I can say R36 is equals to okay. So this will give you R36. Okay. And R36, as we mentioned here, this is a function of theta 4, theta 5, and theta 6. So how do I, once you know the R matrix, how do I find theta 4, theta 5, theta 6? So the last step, step 6, would be find theta 4, theta 5, and theta 6 by inverse Euler of R36. Okay. We'll do an inverse Euler of R36. If you have picked these as RPY, then you will do an inverse RPY at this point. Okay. So the first step is construct this, find the risk center, solve for theta 2, theta 3, theta 4, and then we will do the wrist decoupling. Pass this out. This is exactly in a few simple steps. Obviously, this has half the number of steps, but you can write it down from. Okay. So we'll try to do this in MATLAB. We'll pick an example and we'll try to decouple. The reason we call it decoupling is because at this point you're separating. This is position, and here you have orientation. So we are separating the two, which is why it's called kinematic decoupling. Okay, because we solve it in two parts. We assume that theta 1, theta 2, theta 3 will only dictate the position, and this will control the orientation. This is why we call it this as decoupling. This will only happen if three axes intersect at a point. You can only decouple a manipulator where you have three axes intersecting. So for example, in the simplest case where this is applicable is manipulators with a spherical wrist. Manipulators with a spherical wrist can be decoupled. Most other manipulators you'll have to check from the DH if you have a point of intersection where three axes intersect, and then you'll have to work out the decoupling. But in our case, we'll stick to manipulators with a spherical wrist, so you can have 3 degrees for positioning and 3 degrees for orientation. Okay. In this case, what we'll do is when you solve for this, the configuration can be anything. For example, it could be a cylindrical manipulator with a spherical wrist. So for example, I can have a manipulator like this. This is a cylindrical manipulator, R, P, P, and I'll have a wrist here, right? And this will be D6. Okay, this is WC, and this will be D6. Okay. Or I can have, just as we did, a articulated manipulator with a spherical wrist. So what you'll do is you'll work out the inverse orientation, then solve this part, theta 1, theta 2, theta 3, as we did already. Construct the R03 matrix from theta 1, theta 2, theta 3, then find R36, which is the orientation only due to these angles, 4, 5, theta 4, 5, and 6, and then you solve the matrix by doing a inverse Euler. Okay, so this will give you a complete